Concept came, it was 1956, the artificial intelligence concept. But we are seeing the trend only in the recent years. You know why? Anyone? Only why now we are seeing this trend? Sorry? Yeah, God, everything is on top of AI. But how the chat GPT came? Okay, I shall go to the point. Because of VLSI. Okay, the base of AI is VLSI. Because to train large data, you are using the LLMs, like you are using ChatGPT as an LLM, large language model. How it is built? Because we have to train large data onto it. So that whatever entered into ChatGPT, it should give the response, right? To do that, we have to train it. So to train it, we need after passing that. Now you see NVIDIA, right? NVIDIA is pioneering AI because they have the custom chips and like Microsoft, Amazon, almost all top companies are using the NVIDIA GPUs because to train any model you need GPUs. So I am saying this because we should be proud to have who is studying in power electronics, right? Everyone is talking about AI, but the base is VLSI. Okay? Yeah, we will talk. Like main is a graphical neural network and their applications in VLSI. Graphical neural network is a just a representation of our brain. Like neural network, right? Neural network means we have brain, we have neurons. We have neurons in our brain, right? We are just trying to replicate that. Neural network is not nothing but we are replicating our brain structure into a mathematical model. So whatever you see in the AI, the base is mathematics. So we train models onto the AI models that it has a mathematical equation. So I go in depth in the further slides. So these are the agenda for today. Like I do the basic introduction of VLSI and what is neural network and what is the difference between neural network and graphical neural network. Because there are different types of neural networks out there. So why we only use graphical neural networks, why not a convolution neural network into our VLSI? So it has its advantages and the limitations and why we need GNN and then the basic fundamentals of it, and also these are the applications of GNN. Like we have different fields in VLSI because of RTL, verification, timing, the physical design, sign off, many different fields are there. So in different fields we have different applications where we can improve this GNN. So I am going to discuss about that and some of the case studies and what are the challenges involved in it and future directions and what we can do in the future. Yeah, what is VLSI? VLSI is very large scale integration in its circuits. Here, the importance of it is everywhere we see today we are seeing that we are seeing the IoT, mobile applications, and everything runs on VLSI. Without a low electronics, there is nothing is there in this because whatever you see, if you do a program, right, in computer science, program, you will simulate. But if it is not into the real world, it is not used, right? We are, for example, you wrote a web-based application of a mobile. But it is only for simulation. You won't get any use, right? So when it comes to the real world application only, it will be useful. So everything, all electronics like PC, IoT, and now what are the latest technologies? What we see, like we are saying, the latest advancements, right? All have a base of VLSI. Without VLSI, we can't imagine our world. And these are the high-level overview. Like VLSI means there are different fields. Like if you are using a mobile, right, mobile SoC, to design that, there are a lot of engineers working on it. So different fields they are working. So first we have I'll do a overall overview. For example, you have like a Snapdragon processor or MediaTek processor, and what about the Exynos, the Samsung processor. These are different companies which they are doing preparing coming into the market with the SoC. When you want to buy a mobile, right, you just see the specifications. Is that like on which nanometer is working, like 4 nanometer or 3 nanometer. So what the graphic processor, like because you are playing games, right? So you see the CPU performance. So in Apple also buy one CPU. So that's also an SoC. SoC means system on chip. So the entire system is integrating onto a single chip. So whatever our system, now we can see that previously, like 10 years back, we are only doing the system. Like the computer, if you want to do a presentation or anything, we do everything on the system. Right? But today, whatever you want to do, we are doing on the mobile. How is it possible? Because the SoC, what are the functionalities, what a system is doing, they are integrating onto a small chip. So based on that, we are using everything in our mobile. We are seeing around 8 GB RAM also in the mobile phones. Previously, it's only 4 GB like we are seeing in the systems only. So this is possible because of this SOC. We are integrating all the system into a chip. So here first we have a specification, like a product if you want to launch, right? First we have to have a guidance idea. Like what is the target audience? For example, if you see different processors, some processors are targeted only for the performance, like for gaming, high level gaming. So for some processors only for photo image processing. So if a company is launching a chip, then they have a particular specification on it. So what target audience we have, like a target customers we are going to target. So based on that, first we bring the chip, we do the power, like on which nanometer we are designing, what is the end technology and on what application we are doing. So after that specification, we have an RPA. So we use regular coding. Like initially after the specs is done, we do the regular coding, like all the front end is on the regular coding. Now some advanced companies are doing on coding the system level. Because system level can use both using both verification and design. So based on the specification, we do RTL coding for a particular application. And then once the RTL application is there, RTL is just a transfer logic because based on you see it always in final students have know about it because like regular coding. In that we just have it's like just programming language. But finally the chip is a hardware which has to transfer into the layout. So whatever you do on coding, right, it should be on a chip, on a hardware. So this code we have to convert to a layout. That's a total process. This is the tape code, what we see. And the end logic of it is called tape code. That's the last stage where we goes to the boundary. So that's what GPS. We deliver GPS to the fabrication unit, and then we get the chip fabricated. Like what are the designs we have doing, it will be fabricated onto the chip. So from here, RTL is a logic level synthesis. So we just have gates, right? Like we have generic gates, and gate, not gate. These are all gates we have. But in the RTL, we have only the regular program. So this code is converted into gates. So that's called logical synthesis. So after that synthesis, we do the physical design. So let's say we have synthesis, right? Like different logic gates we convert. Finally, what's the logic gate? Finally, it's a logic gate is it's a combination of transistors. Finally, we transfer all the gates to the transistors and transistors to layout. So this layout is being done with the physical design. Physical design involved from here, like from synthesis, it's a backend, and from before the RTL, it's a front end. So in physical design, it has a timing also. Like timing is the most critical part of the entire system. Because if you design a most best code and you have best application which is running onto the system also, if it is not timing closer, it's waste of doing because it won't work. Because you heard about metastatic history. So we have basically we have either one or logic. Whatever we do, whatever we code, finally it's 0 or 1. So the level should be there. The logic level is between 0 and 1. The system can't predict and it goes into the metastable state. So these things we try to do the timing closure, and if we don't do this, even the system has an entire functionality, verification, everything passed also, the system won't work. And these timing checks are to be very careful. We have doing before the check. So this comes to the physical design, both the timing and like physical design team, two things are there, like physical implementation and physical design. In physical implementation, we comes under synthesis and timing. Like I worked on that. Like a pre-level, post-level HDA and synthesis. These things FDA do and PD implementation. PD I do like a placement, CDS, routing. These are the next further steps. These two profiles don't go interactive. So in the design cycle, right, we have feedbacks. Like timing is at the center part. Like he will interact with the RTL guy, like synthesis guy will interact with the RTL guy, he will interact with the physical design guy. So there will be multiple iterations of design cycles. Because a chip can't fabricate at one stage. Because at every stage, we feed, like timing model will give feedback to the physical design. So because the placement of the macros or cells, it depends on timing. Because the placement of a cell should be will be there, right? So that should be placement error, like a timing error. If we do placement at a random, without any guidance, then the timing will be worse because the macro is sitting in the one corner and which is interacting to the macro at the other corner of a chip, for example. So there is a wrong path, it is some critical path. So we have to design that with these interactions. So we have to place those closer so the timing should be met. I have told a small example like two macros, but there are thousands, millions of transistors there. So it's a very more complicated circuit. That's why these graphical neural networks we introduce because as nanometer technology is moving ahead, the system becomes more and more complicated. Because analyzing is a bit more difficult, and also the frequency. Frequency is the most important thing. Because you see that 3 GHz, 3.5 GHz, these are frequencies you have heard about during the specification by the phone and but that is very important because timing owner will face a lot of issues because of frequency. Because frequency means inversion of its time. For example, 1 GHz, like frequency, for example, like they say 1 nanosecond is a time period. If it is 10 GHz means it's 0.1 nanosecond time period. So the time period gets reduced. So the time to respond to the system will vary. So the system should respond quickly and have to close the timing in that time frame. If it is not, then the system won't work. So the timing plays a crucial role because ultimately the PPA, power performance, depends on the frequency also. Because if you have a low frequency chip, no one would buy it. So the companies also will target and they promote that with the high frequency. If there is a high frequency, the demand for the chip is more. So finally, there are two types of verification. Here you are seeing the verification, right? Physical verification and the RTL verification. Two kinds of it. Like RTL verification, it happens during the RTL design. Once it is coming before the synthesis, right? RTL guy will interact with the verification guy, and those two people will close the system verify. Verification is done with the system verify. And from there, once the code is perfectly verified, the synthesis guy will get a notification from the RTL guy. From there, this physical verification, we have DRCs like design rule checks. Because only will give some specific rules. Because you have learned about the masking for photosynthesis, like this is a process to fabricate a chip, right? So the bit of the transistor gate, these are all going to be fabricated on the silicon. So these things like TSMC and Samsung are two major foundries, like TSMC is a major player. So these guys will provide you the DRC rule checks. Like these transistors should have a distance width and there should not be crosstalk. So from one bit to other bit there should be distance spacing. These kind of rule checks will be given by the foundry. So the PV, like verification engineer, will take those rules and the physical design guy has done the placement, synthesis, all these things and timing closure will be there. Parallelly, this verification guy will do the PV cleanup so that it should meet the specification what from the foundry. So once all this is done, then we go to the depot. We say that this here the chip fabrication is over. I am very happy, but the real challenge will come further also because once the chip is fabricated, right, after fabrication we will only will get the chip again, so that we have to test it. Because once it is fabricated, we have to check how we can test it. From there, the testing will do scan chips. You have heard about scan chips, right? During the time closer to the design only, we need to scan chips so that when the pattern is propagated, once the chip is out, they propagate the patterns and they will check is the chip is working properly or not. So finally, once the chip is done, we say that the code is successful and the product will be launched onto the market. So this is the overall view of this. And the key challenges I told you, right? Complexity. When it is going to nanometer technology, the designs are becoming very more complex. Power consumption. Now you see that AI technology, you see like big data centers. But the major challenge in the data center is power. More power. According to like one of the studies, a one power data center can consume the power of entire city. So only one data center. So that the huge power demand is there for AI. So we have to design a low power design where it can consume the less power and deliver the most of the output. Yeah, this is the overall flow what I explained, like artificial is functional, and from this is the code, right? From this code, it is going to the logic gates, and the logic gate finally into the layout, and layout to the fabrication of the silicon, and finally it goes the packaging. So introduction to neural networks. So I told you, right, like neural network is just a neuron, like how we are thinking. If some like for an engineering or anything, we have some lessons that teachers will taught us. So we learn that, and if you do some mistake, right, we are remembering that mistake and we don't repeat that again. That's the basic functionality of how we learn. The same thing we are integrating onto the systems. So I'll show you a diagram. This is a neuron. So this is the basic neuron what we have in our brain. So here just replicating that would be a neural network. That's a basic function block of a neural network. You see, these are the inputs and these are edges. This is the activation function. Activation function, like in our brain also, we have just as mathematical functions. Everything in our brain is a mathematical function. What we remember? We remember something by calculating something in our brain. So the same thing, this activating function is there, right? If you want to train a system, we have some equation for it, like a non-linear equation, I am going to discuss in further slides. So that the system will train according to the activating function, and it will set the equation based on the activating function. So that the system can identify, for example, ChatGPT is there. For example, you ask some question for the ChatGPT, write a code for a hello world, for example. So you are getting the code for the hello world. But what actually happened is, it is trained before. Because if you want ChatGPT should do some response to it, it should be trained. There is two concepts, training and inference. If you want some model, if it has to infer, it should train previously. So the training can choose a motor. That's what now everyone is studying for the NVIDIA GPUs. Like if you see the news data, Amazon, Microsoft, everyone like the Blackwell is the latest data center chip from NVIDIA. So every company is struggling for it to get that chip because that has a high throughput and the number of token handling is very higher compared to any other chip in the world presently. So that chip will train these activity functions and it will make the system ready for the new data. So once a question is asked to the activity and anything, it will have that training model ready, and once the input is passed on to the activity, it will go. So perfect order behind this. And like in the neural networks, right, like we have the nodes like neurons, as discussed in neurons, we have there is a structure of three structures like input layer, hidden layer, output layer. Like I showed you, right, like inputs are the input layer, and the activating function is the hidden layer, and output which we are getting is the output layer. These are the three main functions. These are overall view, but the internal hidden function and hidden layer can be multiple things based on the complexity of the application. Because I showed you a small example. But there are 3 or 4 levels of hidden layers will be there. Where it can train and the activating function, there is a back propagation. I will explain that. Based on that only the neural network will be trained. So input layer just has the starting point. It has a for example, take as a starting. The input what we are using is input layer. The hidden layer, the activating function and everything is in the hidden layer, output layer. And finally, the prediction output we get from the output. And these are the neurons, nodes and data activating functions. Here, these nodes are there, the circuits which are called as nodes, and the centers are the activation function, and these are the weights. So based on the weights only the calculation is done actually. So I told you right that training and inference. So the process based on the once the system is ready, right, from the multiple iterations, the neural network will be trained. So we do see the control systems. Right? We have a control system where there is a feedback loop. If anything is there, we give a feedback. For example, if we have something we are propagating, and we have like for example, desired frequency is for example 1 GHz, but you have a 500 MHz as an input. So the feedback loop will loop it, and the error message will come as an input, right? Again, it will train. So that we have a feedback problem here. Like I will give an example to understand. Because when there is an error, right, when the error is taken as an input, and this input is taken as a feedback to the system, and again we are training that so that our desired output we are getting to the feedback. The same thing, the back propagation, what happens? Once you send the data right into the neural network, it will calculate the error at the output. So that, for example, 1.6 is the, for example, 1 is the result and 1.6 is the output. What? Why? Because we have 1.6 error is there. So that data will back propagate onto the neural network. So that it will, these weights and accuracy function is there, right? So these things will change, like until the training is done. These weights and accuracy function variables will be changed. That's what training actually. Basically, back propagation input, these functions will be iteratively trained so that at the final output we should have the desired output what we want from the accuracy function. So see that's an iterative process. So that it's taking a lot of time and power to train it. So finally, once the neural network model is ready, we can ready. That's the last step. So that the ChatGPT, anything what you do, it's already trained. So once it is done, you will get the desired output. So this is one of the basic block. So here you see the equation, right? Like W is the weights and X is the inputs we are giving. So B is the additional non-linearity what we are adding. Because these weights will be changed from output, right? It is back propagating. These weights will be changed based on the input. So that the training happens so that these weights and this equation comes when the result output, when we get that result output from the accuracy function. Now these are non-linear, what I explained. Like if it is a linear function, like for example straight line, there won't be any difference actually. Whatever you do, for example, what I say, if you ask write a code for Python code for multiplication, for example, it is a linear curve, right? And it will give output for all for the hello world. If you whatever question you ask, it will give a hello world program because it's a linear curve. Because you are training only the one model and you are not giving any variation for it. So that whatever you just imagine that whatever ChatGPT asks for, it is giving only the one answer. That's ridiculous, right? Based on using ChatGPT also. The same thing to you different answers for the different questions. It should be trained with the different sets of data and different academic functions which has that. Because of that, we have invented non-linear. Because plus B I have shown it in the previous slide. So that will give the variation for different inputs, what output should be generated. So based on that, this non-linearity we should introduce so that the system will respond for different inputs and give different outputs which are accurate. This is one of the typical neural network, what I told you, right? Like this is the input node, like this is a hidden layer. This is the input layer which has like multiple inputs. But this is a complex structure where we have the time where it happens. Because we have different nodes right here. These are nodes and these are actually functions. So what I showed you the basic drilling node previously. So these kind of different activating functions are introduced into the hidden layer. So that when, for example, here first input is an hello world program and the second input is a multiplication program. Third is like addition program like simple things and everything. So you have different inputs, different programs you want. So when you pass on to the input, this goes into the different hidden layers of this neural network. So that based on the input question, it will go to the different models and these activating functions, like the calculation what I told, right? The weights already the model would have trained. So based on that, we predict the output and we get the output from the chat. So finally, now I explain about the neural networks. But why only the graphical neural networks? Why not other neural networks? Because there are different types of neural networks. One is a convolutional neural network, this is a structured neural network, and graph neural network. Because convolutional neural network mainly deals with the images. Because I have done a project called convolution using basic mathematics and images. Because in that, like mostly multiplication is there. Because you guys also know, right? Like graph theory, we have about matrices, we study many lot of concepts of the mathematics. Because never we think about why we are using it. Because we have matrices, we are studying for the modeling, not all, okay? Just kidding. We are studying and we don't know the application. What the basic application, what we are using. Like once, like what monetization is when we are studying some concept or anything like matrices, why we are using it. every mathematical concept what we are learning has a bigger applications in the real world. So matrices are very important. So the matrix multiplication and all these things are happening with the matrix concept. The entire neural network. So based on this in convolution, we use if an image, if you take an image, right? Image is nothing but the pixels. So pixel is has particular amount of data. Every pixel has, for example, 8-bit binary data. For example, if you want to represent 2, right, 0, 0, 0, 1, 0, these data will represent. Like all the images are represented in this like binary data, and the processing, whatever the image processing, what we are seeing today, are happening because of the convolution system. What happening? So, but in VLSI, right, we have an AND gate or gate. So these are gates which are just like a network. So this network actually, the graph and neural networks will store the data about the previous like intermediate connections. For example, I will show you slides further. Graph just has a nodes and edges because they are connected to it. Just in, if you see the schematic of any like diagram, for example, NOR gates are there, right? They are connected into the different combination circuits. So just as the nodes are connected to edges. So both are same. There is a similarity in the graph and neural networks and the our schematic systems in the VLSI. So we are using graph and neural networks for the VLSI. And these why children see because graphs are there, right? They are not bits. Because all the convolution is there, right? If you image if you take, every pixel has some data. So they are fixed actually. It's just why. But in graph and neural networks, these are not grids. So, for example, I have told you a macro, right? A macro which is at the one corner of the chip, and a macro is at the other corner of the chip. So, there may be a connection of other macro at the other corner. So, we can extend that. If you want to introduce some connection in the VLSI, so we can easily introduce one node and analyze data from these interconnection relationships, and so that we can predict that what is the timing of it, what is the wire length, what is the capacitance. So all these things we can analyze based on the graph and neural network. So we are doing. So this is a variable set. I told you, right? If you want to add some new cells, new macro, you can just add it to the graph system, so that we can analyze further. So permanent combination, no fixed reference, like starting points, like whatever it's a variable, it's not fixed. So that, for example, we have some functional issues. Because what is engineering change order, right? Functional issue means once we have designed some system or functionality, but you want an additional feature. Actually, you want an additional feature on this. So we give some functional issue. So that that regular code is added to the synthesis block, and we do a timing analysis on that. So here, as basically the character cell structure, leveraging information, and nodes and edges, the same what I explained. And this is the one of the typical neural network, which has a character structure. So here we have the input, right? These, for example, this is an AND gate, NOT gate, OR gate, for example, which are constructed with a graph-like structure. So if this information is passed on to the graph and neural network, we have the data, what we have, the wire length, capacitance, everything is there. Based on that, the neural network is going to do the output. What's the desired frequency or synthesis, like where to place the cell. Like is it time related or physical? We have two types of synthesis: physical level synthesis and non-physical level. For example, floor plan is there, right? Physical design engineering will do the floor plan of macros where to be placed. And since they will do only the synthesis. So, for example, if you take the floor plan as a feedback input to the synthesis, so that the synthesis guy can know where to place the macros. So that if the proper macro is placed onto the particular location, so the timing will be better actually. If there are two macros that are far, it is based on the floor plan feedback, those two macros will be kept near, so that the timing will be met for those two macros. And seeing the macro for an example, because the system is a highly complicated design, so that these kind of macros will be thousands or lakhs will be there. So I will just give you an example. So how actually GNN works? So in the process, like the data is embedded into the node location. So we are constructing basically to the input layer, hidden layer, or output layer. These are the main building block. But these are building blocks for the neural network and graph also. The main difference is we represent those data in the graphs. So here this is a rectified linear function. This is called activation function. What I told you. So based on this function only, the neural network will get trained. These are the deep neural networks. Any questions? And GNN model representation network such as a web protein, the same thing. Like the concept of neural network and graphical neural network is the same. But the main difference is the graph which we represent. I will do an example for the object. So I have illustrated three differences. Like we have three different graphical neural networks. So mainly graphical neural networks we use for the social networking analysis, implementation for social networking. Because if a person is there, he is connected with different connections. So a person has a different connection information of other nodes also. So for this social networking, which is similar to the VLSI, because in VLSI also many resistors ability connected to the different resistor transfer model or get something. So every node has the information of the other nodes also. So because of that, we are using generally VLSI. So RNN is a natural language processing, just as analysis. So if you are giving a textual strategy, right? I have program for the division or everything. So it is a sequence of data which goes into strategy. So there RNN are used. And coming to the CNN, it's just an images where we do the convolution of this and this image processing what we done on the convolution is due to the CNN. This is the difference between CNN, RNN and CNN. The fundamentals of GNN. Like I am going into deep of what GNN has. It has nodes, node features, edges, features and graph structure. These are the basic nodal structure of internal graph data. Here we gather the information from the neighbor sector. So based on gathering the information, we are updating the like active functions, and these processes will be created till the training model. Here in node side, we can now relate to the VLSI nodes. Here we have gates and cells in VLSI. In normal, if you see the Facebook, right? In Facebook, Instagram, anything, these connections are nodes are represented with other persons. Like a person is connected to 10 people, right? So he has a connection with the 10 people. So based on his connection, we can analyze that whom he is talking. Like what is like many people say a person is in Facebook or anywhere we are having the surveys like who is going to win the elections, who is going to like which RCP has more fans, like CSA are more fans. These are data is there, right? So these things are also analyzed by the neural network. Just as if a person is connected to the 10 people and 6 people are RCP fans and 4 people are CSA fans. So here the same data the 10 people will have, right? So it is a huge network effect. So based on this, every node has a particular information of other nodes. So based on that, they will analyze the data. Which are, like I have in the fan base, like these are also using the drug delivery, like because in molecules, right? In drugs we have molecular structures, different molecular structures. So based on every molecule has the data of other molecules. Like if you combine one molecule, what happens to the reaction, and this huge data. So these things are applicable on those applications also. So these are nodes we keep gate cells, cells and pins. And node features is a gate type area. So if a gate is a node that it has a node feature, right? So that is stored to the vector. So this node has a gate type like which like P type and N type we have, right? And the timing delay of area, like every gate has how much area, because the timing delay and area we have, then only we can know that how much chip area we are going to fabricate. Because we have version 2, version 4, version 8. These are the drive strength which we are using the different gates. For example, if you want to like 400 micron net length is there, for example. So one drive strength inverter can't drive 400 micron length like out. So that we have to use D8 drive strength inverter. So inverter not buffer. So if you want to do the D8 inversion or buffer, if you go to the internal structure of the inverter, we have two transistors, P type and N type. So we have W values, like bit to W ratio. So if the bit is more, the number of current ID equation is there, right? Based on ID equation, if more current is there, you can drive more net length. So if you increase the bit rate, it is then more than, and the area is also getting For example, you have a length of volume 100 micron. But if you are using D8, it's waste of area, right? Because then the system it should predict that there is no need of the D8 like divider or buffer. So that it will size it to D4. So that, for example, the same condition has 400 inverters, right? So that 400 inverters are there, which needs D4. But if you use D8, double the size will be. So we have to reduce the size of the chip. Because the size is a very constrained thing, because in mobile, right? We want to integrate the small chip into the hand device. So to do that, we have to reduce the size as much as possible. So at that analysis also, these parameters we should have actually for writing the GNN data. So these edges with the relationship between the nodes, that is a net and connection. So like which buffer is connected to which inverter or which gate, these information we have in the edges. So based on this only the analysis moves in progress. So these edges will have the features, like edge means it's a net. So the property is what the net has the edge features. So edge feature has the width and capacitance. Everything we have right. We have two things in the net, like input capacitance, input transistors and output capacitance. Based on these two things only, we get to decide what is the net, delay of the net. Because we have two delays, intrinsic delay and extrinsic delay. For example, one inverter is connected to another inverter with 100 micron net. So how this delay is calculated? Actually, there are two things are there. One is that cell delay, another is the net delay. So cell delay comes based on the inverter, like inverter W by M ratio and everything. The net delay based on the net length and the input transition output capacity. So if it is a good drive buffer, then the transition will be very easy. But the output cap can't load, for example, D4 inverter can't drive the D8 because the load will be high. Because there is a capacitance in there, the equation will have. So based on these two delays will be calculated. Because in the timing report you will see that. For example, when I am analyzing the timing reports during my project, the same D4 to D6, for example, D4 is connected to D6. The same has a 50 phase delay and same has a 100 phase delay. So same cells. Where the difference comes here is the net length and net property. So that extrinsic delay, which is the net delay, the capacitance of the net is more in other cases. If it is more, right, the delay of the net is more. So based on that, we have to decide, we have to use the break strength or we have to break the net. These are the fixes what we do in the net. So this is a graph structure, like here, as in matrix. I told you that matrix is the important thing. Every work, these mathematical operations, everything we do involves the matrix operation. So these matrix use the connection between the different nodes. So I'll give one video also that gives more clarity of visual representation, how we do that. And these matrix include entire information, like how many nodes we have. Because one inverter can be connected to two buffers or three buffers, anything, because system is very complex. Based on the functionality, connections will be there. So based on these connections, we try to represent the whole data into a matrix. So that by using the matrix, we can reconstruct the circuit. I'll show you one of the examples where we can convert this is one of the structure. See, if you see that this is just inverter, which can be connected to the graph. So any structure, if you want to do the graph and linear analysis, that should, the normal circuit should be converted into a mathematical model to a graph. And this is one of the examples. Here, all of the registers is the C1 is the combination of this. So in the timing analysis, right, we do the there are four types of timing process. Like into range, H2 range, H2 out, P2 out. These are the four types of timing analysis what we do. And we have the interface timing. What means interface timing means SOC is not just a one block, right? Just we have audio block, image processing block. Every block is individual, but these all are being interacted. So once we have, if you take a picture right in the phone, what it does? First it should capture our image, and like we have some image enhancements. So once you capture the thing, it will process these all the data into the chip. So here the image processing will be activated. For example, you want to listen a song. So then the audio block of chip should be activated in the mobile source. The same thing, these has interactions, right? So the timing controller between the block to block interaction is called interface. So So between block to block, you have to close the timing, and internal to the register logic also you have to close the timing. So these are register, here to here, and input out here to out also. If I am not going to the calculation, so when we go to the calculation, we see the setup and hold, right? Basically, at a time is based on the setup and hold. So based on the equations, we close the timing, and if we convert this element into this graph, here what are the components what I have explained, like net length, timing delays, these are all the components of a particular set. When we integrate that into graph theory, every node has the information. By example, this 2 is the register, what we have here. So here this register is connected to the C2, C1, C1, C3, and C2, C3. All these connections are there. So how much delay, like we have to calculate the worst that's a critical time. In our life also, right? I'm just relating to the life. If you face the biggest challenge, in your life, if you face the biggest challenge and if you overcome the challenge, right? Then other challenge will be very light for you because you will be more stubborn for the big challenges. The same way in the system also. If you close the timing for the worst part, it will be made for the other parts also. So that's the actual concept we say that as a pessimism. Pessimism is the worst thing. So that if you close the timing at the worst critical level, once the fabrication is done, it should work at any point. So just relate this VLSI because VLSI systems are just go ahead. We can relate to our life system. Right? If an exam is there, if you prepare at the topmost level, you learn every concept and every question in any subject, then any question if you attempt even at the best level question also you easily attempt it. The same way, we close the for the worst case scenario. So how to calculate the worst case scenario? You should have the information of every node, right? Based on node only, where the connections is there, what is the delay. These are all calculations based on that only. Which path has the worst timing path, you get to decide it. And we analyze the timing path and we close it. So that we have different corners also. This is called PVT corners. So these PVT conditions will be there because at different temperatures. Because temperature is not good. Today, maybe 35 or it will be 45. Because when the temperature gets increased, so the electrons are there, right? So they move faster. There will be collisions. So the mobility will be based. So based on mobility, ID current will also be. So based on ID current, the relay should be because everything in electrons is interlinked. If one parameter got changed, it affects many other parameters. So we have to analyze all the other parameters and we have to close the timing of this and everything. Every aspect we have to close in different corners. So this is one of the examples. Then this is another example. This is like I told the code, right? Once the RTL Bengaluru code is there, so that is connected to these gates. So logical gates. So from the gates, we have to convert that to a graph data structure to train the graph general model. So I am taking one just example to explain this. See here we have nodes for AND gate, OR gate, NOT gate. So this is a small graph which we have, which has 3 gates. So we have to get these nodes are the basic gates. What I explained to you. So here these nodes have a particular features. What I told. Nodes means like whatever properties it has. Every gate has some properties. So how many property variations what we have which integrated, that much best is a feature. Because we have more parameters, right? The rectangular type will train much, and if any variation is there in one particular feature, it will relate to the other feature because we have activation function. The activation function we design with the ID current. We have different functions what we have in our study subjects like ID current equation, UNCF mode, omega, WA, speed, and everything. Indicate that to the activation function. If some function got changed there, the activation function gets automatically changed and equation gets changed. So based on that, we decide like what is the critical path, is it the same critical path, and is it other critical path? Is it the change of phase from the other? So these are 2 parameters I am taking, the area and the timing. So these we keep it vector. And coming to the edges just use the like connections, like how many connections are there, where it is connected. So every node has its own properties and also where it is connected. Based on the connection, we can get the information of the other node also. So this is the feature that I have updated the wireless capacitance. Here, previously I told about the cell capacitance. So timing delay and I have done timing delay. Here, wire has a capacitance. This is the property of the wire. It has a connection. This is capacitance in the other feature. So this is the graph. I told you the adjacent matrix. Right? This is the property. Here A, B, C are there, right? Here A and B. These are connected. I told you right? A is connected to B and B is connected to C. So how we represent the connection? Here A is connected to B means we are keeping one as here. There is no connection between A and C. So it is 0. And B is connected to C, right? So this connection is kept as 1 in the B to C connection. So that this is a very small representation. When the systems become more complicated, then this matrix becomes more larger. Because this is a 3 nodes, so we have 3 basic matrix. For example, if you have 10 nodes, you have 10 by 10 matrix. So that's the criticality of systems. Because if you go more and more deeper into the technologies, like wire technology, you have billions and billions of parameters. So for every node you have to analyze. So the complexity will be increased further. So that's why we are training models for the graphics matter, so that we can predict. Because in the industry also, right, we do floor planning. Like since this will get the net from the RTL. So it senses size and will get the PLRTL. So based on the previous data, they will give normal floor plan as a basic one. Because we have different stages of modeling the system. So it takes around 6 months to 1 year for the project to complete. But every stage of the project, this feedback loop, like because we are giving the net list, we are analyzing the timing, and we give the feedback of PLRTL. PLR means place and route. So they will place the cells. Like like 2 types of placements is there. One is the SOC level here. Because on SOC have, for example, 10 blocks. For example, audio block, demonetization block, and video block, video processing block, these blocks. So top level they will do the floor plan. Like he will out the area. For example, 100 units for audio, 50 units for video. Based on application for logic level. Once they fire one time initially. Because individual block corners will give a synthesis at least, and top corner will find all the conforms. So that he will get the overall timing area, like how many cells are there, how much area of the cell, everything. So based on that, he will give top corner will allot the area to the particular time block. So individual block corners will appear around will be there. So they will be the internal one because macros, cells, everything will be there. Right? Initially, these macros will be there. Macros are the hard logic IPs. IPs are different and logic cells are different. IPs they will place around the boundary of the corner because the logic levels will be interacting with the macros. So that if you think you place at the center, right, then they will place the logic levels. You can't be placed, right? Initially they will place around the boundary logic, and it's the fly length. What we call the fly length. It's not this terminology, we call fly length. Fly length is connections. Node is there, how many connections are there? So based on that, they place some of the what's the initial flow. So that there is the timing at least stage level. Once the placement is done, CTS, like CTS is a clock based CTS. Initially there won't be any clock. So once this placement is done, at least the timing is done. I told you the timing is very important. Like if the timing is not met, you can throw the chip out. So this CTS once there are different tree structures because the clock should clock it evenly because we have a concept of Q. Because there is a difference between launch and capture delays and drop of delays. Right? That's not Q actually. So that's why useful Q is there. Because setup and hold are two things which all will do. Because if we try to fix the setup right, we end up with having hold options. The reverse is vice versa. I saw a meme actually, like one day, like just try to follow meme pages of VLSI. Because I try to enjoy the concept by using the movies or memes. Because when you see that memes, right, you can try to enjoy the meme and also you can remember the concept also. In that, actually, one man will be there, one actor is there, right? He is trying to open that map actually. But it is a road map. Road map, he wants to try to open that map, he is moving front. But because it's already road, right? Other time is coming road. Because he wants to roll out, something he wants to stretch, other one is good. Again, other one he wants to stretch and this side is good. The same things happens in the timing. You want to close the setup, right? Always there is a very small code. So that we have to check like different cells are there. There is a variation between setup and board. A cell will have a 10% variation in the setup and board. And the delay cell we have these delay cells. They have 20% variation. So based on the variation, which cell we have to introduce in the like a timing fix that the timing board will decide. So based on that, we have to decide which cells to use. So the setup and mode conflict is there. Based on that, to check the setup and mode conflict, these actions are very important. Because in one path it may be set up here, and another path there may be both. So we have margins. Like we are setting things set up right. We see that the whole market is check. So how much gold is there? And there is a concept of cross push also. That we go at the last. First, how we fix this data path optimization. First, directly we have to optimize everything data path, and then only we have to go past the clock, because clock is very sensitive, right? Because the clock will go to many modules. So against few issues. So these many things will come. So first we try to optimize all those things. So to get the optimal layout, optimize thing from initial thing we have to get the constraints proper, the constraints in initial stage of the project. We have multi-cycle path, single cycle path, false path. These things are there. Right? These are some timing constraints. So these constraints we have to properly design for the system. For example, you have a false path at like one point or other point which has a 100 nanometers. But it is not a false path. By mistake you have declared it as a false path. But if you disable the false path, thousands of violations. So that's a very critical part in the time. So the constraint should be very clear and should be signed off to this. Because one parameter will change in the time constraints and lakhs of values. So that you have to time close such a particular. So I gave some video. Yeah, this is the overall summary where we have like nodes, whatever I explained, I just kept the edges are ends and features are ideal. These are kept in the one of the vectors. Based on them, we have. So why we need generative VLSI? These I told you because of the graph-related similarity where we have in the huge network. This graph generative VLSI. That's the main advantage because of complex designs. If you already convergent network, the rate is good. But if you want to add some 1,000 cells, some 2,000 cells, you want to vary that network. If you want to vary that network, you should have a graph-like structure to incorporate it. So here, logical synthesis. So logical optimization what I do. From here onwards, I can like we use the RTL language, right? So we do the synthesis. So physical aware and non-physical aware. Placement aware, like these things around goes up to 3 or 4 months actually. So the hardest part is the floor plan because the PNR the always try to change. So here we have. PNR tool like we use synopsis and data. Basically, the impression we use synopsis IC2 or SC2 compiler or in the cadence tool. In that, you heard about Bogian? Like Bogian instructive tables, just like a chess game. So actually, artificial intelligence bot has defeated the world champion of Bogian because Bogian is just like chess. So Google has a artificial intelligence model where it can significantly deep mind actually. Google has a deep mind algorithm where it has defeated the Go game. Go game is very similar to the floor plan because where to place the pebbles. So that's actually the reason. So that concept is used for the floor planning, like where macros should be placed. So that algorithm can be used in VM. So this logical optimization is like technology mapping. Because we have 4 nanometer, 3 nanometer, 2 nanometer, like every technology node, we have different cells. They are shaping cells. So the technology is different. So initially, normal boards are gate actually, normal and gate one. But the and the R gate are having different flavors of it, or different technology. Different technology mapping is there, right? So the technology mapping is done to the particular item, the AND gate only, which has 4 nanometer, 5 nanometer, like a 2 input NAND gate, 4 input NAND gate, 8 input NAND gate. Based on that, this gets set. But normal initial mapping, initial instance is AND gate means just we have AND gate is the, for example, RTL logic, right? Just AND gate is not guess inside. Once the AND gate is there, it is mapped as a technology map. So based on that, for example, 4 input AND gate has more input and more delay than 2 input NAND. So that the delay calculation everything gets there. So this is one of the mapping. Now what is these are original netlist and SSG and transfer. So based on these nodes, we get how many inputs are there, how many connections are there. Those properties will be playing this unit. So this is one of the model input. So from input to graph to circuit conversion, once the circuit is converted, here the GNN architecture, which algorithm what we have in GNN, that is get trained and embedded into this, and the hidden layers, the data is going to the hidden layers, and then based on that GDA task we have. Mostly these GNN tasks are everything available to the EDA tools. EDA is mainly synopsis and cadence because they have the tools and we work on the tools, because once these initial placement, all these things are done, synthesis are done. On top of it, we do the analysis. Any doubts? Anyone? To industrial related anything? The graphical network just as a brain, I'm saying you showing the connection. Just as a brain, how our brain works, same similar kind of thing, these modes. Just imagine under organization a complete circuit design, which are connected in this way. So I'm going to then this video will do the basic presentation.
Can also be used to find new drugs for other diseases like cancer, improve transportation, solve problems related to social networks, and many others. But what is a graph neural network? Let's find out. Imagine that you're Cupid and, oh, hi Andy. Okay, so you've been tasked to find a suitable match for Andy to fall in love with. How would you approach this?
Hey, still thinking about joining the 30-day Python using AI bootcamp by AI. So what is it? 30 days you would go from going?
First, we know Andy's age, gender, occupation, that he reads fiction, loves cycling, and he can't dance. Well, that's a bit harsh. How about his learning to dance? Let's place all these features about Andy into a list as such. Next, let's gather information about his social interactions. Who does he hang out with most often? And who are some friends of those friends? Alright, we can now begin to analyze this.
Yeah, here you will see, right? You can just, this is an example of a social network. So just declare those people with this account. So that his matrix is there, like he loves cycling, these parameters are there, right? Just replace that with the wide length, capacitance. So same thing we have to interlate with this concept of paradox. The concept is same. So this graph theory can be as a multiple application, but we have to correlate with the system circuits.
This web of information to find handy a suitable match. This web of data can actually be viewed as what we call a graph in computer science. But what is a graph exactly? A graph is a structured way to represent data. It consists of nodes to represent entities like people, and edges to represent the relationships between these entities.
These two are just nodes are our gates and edges are our relationship between different nodes.
Like in NVIDIA's network, each node might also have a set of features which describe it. For edges, they could either be undirected, meaning two-way, or directed, one-way. It's not difficult once you get the basic mechanisms. So let's stick with undirected edges for now. But why graph neural networks? If you're watching this, I'm sure you've heard of the expansive success that neural networks have had on many problems. They are able to learn a variety of desired outputs from several types of inputs, such as numbers like stock prices, words that we use every day, or even images like this low resolution photo over here. So why don't we just feed Andy's network through the all-powerful neural network and let it tell us his best match? Well, it turns out that neural networks have mostly been successful on more structured data types. For example, numbers belong in a series, words that we use every day are found in sentences, but neural networks still struggle with more complex data such as graphs, which do not have any fixed structure or ordering. So, in order to reason with graphs, we suggest going back to the drawing board to study what made neural networks so successful. The first layer in a common convolutional neural network takes each pixel and
This is similar to our image data. Actually. This is a convolutional neural network which is going to explain because these ones and zeros are there. Right? For example, we say like a black and white picture. For example, say black is 0 and white is at 1. So the entire picture is divided into the pixels. So each pixel is coded into one data. Here two values are there. For example, if we have 64 colors, for example, like different variations of it. So 8-bit data. So 8-bit data is coded into this, and in neural network we pass on to this. So we can see this carefully so that we can understand how image processing can be handled.
extracts information about its region by aggregating the pixel within the context of its neighborhood. The next layer then extracts information about that region within the context of its neighboring regions. Doing this over enough layers, the network will be able to reason over different parts of the whole image. And then with some linear computations, it can finally identify the relevant object. Take a second to think, how might you apply this mechanism to graphs? If you look closer in the image, you can actually view it as a special type of graph. A grid graph that is structured, and every node is a pixel that is connected to its 8 neighboring pixels. Seeing it like this, you might think to yourself, why don't we just use the same aggregation mechanism that we've seen before? And you're right, we can actually use that same intuition on graphs. Relaxing the properties of fixed structure and ordering, we can similarly gain a better understanding of each node by aggregating the messages received from all neighboring nodes. Now, hold on to your new message, Andy, as your friends complete their first round of.
Here, the message passing is similar to the data what we pass on to the system. Because the 0 or 1 we pass it from register to register to the knowledge. That this message is similar to the data what we pass on to the system.
Message passing. Observe how the color of each message changes to represent the newly aggregated message. And with each new round of message passing, more and more information gets passed around in the graph. Over sufficient rounds of message passing, we will eventually obtain a final representation of each node in the graph that will describe it given the larger context. Now, we can actually also view the rounds of message passing as a series of layers, just like in our convolutional neural network. Here, we go from the input to round 1 of message passing, and then round 2 of message passing. And
I told you that there are different layers. Then these are the layers actually. Like in one layer it will train and the after output is come on to the other layer. So every layer has their actual functions. So it will train the model based on the particular actual function and will get the result of it.
this produces a final understanding of nodes. So we now know how to understand each node better. But how does this allow us to help Andy again? Well, as humans, we might take a look at Andy's graph and mentally or visually we will process all the information such that people who are not compatible with Andy will have a stronger association with him. In other words, in our mind, maybe people who have similar characteristics to Andy will be placed closer to him, and they are therefore stronger candidates. Similarly, in the process of reasoning over a graph, the graph neural network seeks to summarize all the information of each node into a numerical representation, where nodes which are more similar will be closer to each other. We call this representation of nodes node embeddings, and we call the space of all possible representations, you guessed it, the embedding space. But how does the network know how to come up with these embeddings, and where to place them in the embedding space? Neural networks need an appropriate, measurable objective to guide the network into learning something useful for our task. In Andy's case, one way to tell the network that embeddings of people who Andy spends a lot of time with should be closer to him. Rearranging the expressions, we can quantify our objective into a loss function to tell the network how well is it doing. Adding in all the other objectives from other nodes and taking the average, we now have a working loss function. We are finally ready to see how all this comes together to find Andy's match. Firstly, from the input, we forward propagate through the message passing layers to get a final representation of each node. We then tabulate the loss and back propagate it through the network to tell it where it went wrong.
This is what I explained. Because we give the data as input, right? That's the forward propagation. So this goes into the different layers and we get the data here. So based on that we calculate the loss, like what are different error. So based on error it is going to train the model the activity function. This is back propagation. You see right, this data is back propagated and you try to reduce the loss, like that is the error. So that the final, the multiple iterations, finally we should have the less error as much as possible so that the gene network will predict the electronic design systems accurate.
The network changes its computations and tries again, this time hopefully with a better performance. We can do it as many times as we want, and after the network has learned embeddings of Andy's graph that are good enough to meet our objective, we could simply shortlist a bunch of people who are in a certain radius from him, maybe filter out some Andy deal breakers, and rank them as potential matches according to numerical distance. And we are done. Our hopefully successful matchmaking task is actually a form of naked prediction, where we task the network to recommend new potential edges between nodes. Another popular task is node classification, where we use the representation of each node to predict a certain class. We also have clustering, where we break up the embedding space into different groups.
This is some clustering. Actually, K-means clustering, if you heard anywhere, at any time. Like this is one of the algorithm where we use. Clustering is like, for example, when it is related to the circuit theory, right? For example, one set of logic has more interaction than the other set of logic, for example. So these group of cells should be placed in one corner of the chip, and other group of cells should be placed in another corner of the chip, because there is no interaction, but these closed cells has more interaction, which has a timing dependency, the critical part. So that this clustering will help where to place those cells in the floor planning stage of the chip design.
And finally, we have graph classification, where we do some form of aggregation over all known representations of graph and compare with other graphs. This last task was used to discover ASIC. You might notice that the key component of these strategies involved the need to learn good node embeddings. Going back, hopefully you can see that this actually hinges a lot on how we perform message passing between the nodes. So let's dive in to take a closer look at each round of message passing. Message passing is actually a mathematical function, which we call f, to update the receiver node using the messages from each neighboring sender node. In this case, the receiver node is Andy. Note that this aggregation includes the receiver node itself. In most cases, we want to give different importance values to each neighbor. For Andy's case, this could be based on the number of connections that each node has. We express these as constants, since they are fixed by the graph's structure. Similarly, depending on the final task, we might want to weigh each feature of the nodes differently. For Andy's match-finding example, maybe a combination of age and education is more important. Instead of handpicking which features are more important, we can leverage on the power of neural networks and learn them through backpropagation, as represented by weights W. In order to learn more complex patterns, we will also want to add some non-linearity to the function output.
The thing I explained, where the non-linearity is important. So these weights, and you can just get what I explained previously, the net length, the capacitance, all those components, you just get to this, and based on this mathematical function only, the conversion, like graph neural networks are going to work.
Going one step further, must we only use the sum operation to aggregate the messages? Well, since changing the permutation of the nodes don't change the nodes' neighbors, what we really want is a permutation invariant function, which consistently aggregates information from the node's neighborhood regardless of ordering. Let's now express this slightly differently to generalize it to any other node and not just Andy's. Firstly, all the neighbors can be denoted as J, and so we can group all these terms and denote the weights as a function. Since we are updating the receiver node, we might want to treat its node's features differently from the rest. We can also denote the outermost nonlinear function as a general learnable function. And here, we arrive at one of the three general flavors of graph neural network layers: convolutional, where the weights of neighbors are fixed based on the structure of the graph. Previously, we discussed that the weights for each feature can be learned. So, could we also learn the weights given to each neighbor according to their features? Turns out we can, bringing us to our second flavor, attentional, where the weights of neighbors are learned based on the interactions of the features between the nodes. Finally, so far we have been aggregating a weighted combination of neighbors. But the most general form of message passing would be that each pair of nodes collaborate to produce a specific message between them. One final note. We call this form of convolutional message passing. Computing the updates for each node sequentially like this sounds slow, doesn't it? In practice, we can actually leverage on linear algebra. A graph's edges can actually be summarized using
These adjacent matrix, what I explained, this matrix gives the entire information of the connections, what we have to the circuits. It's just as so.
in a table which we call an adjacency matrix. Note that for our case, we will need the nodes to connect to themselves. We can also stack all node features of a graph in a matrix like this. And we now have our three main elements, including the learnable weights, W with all these dimensions. But wait, do you notice something missing? You got it. The importance weights for each neighbor is actually computed by changing the adjacency matrix accordingly. And now, hopefully you can see how these functions are exactly the same. With this, we can now use some highly optimized matrix multiplication library to perform message passing for all the nodes at once. Isn't that amazing? With that, we have come to the end of our introductory graph neural network video. I really hope that it was helpful to you in some ways, and if it was, do give a like or sub.
Yeah, I think we got clarity from the video. So just related to that, we VLSI related stuff because that's why I explained just relating those to the circuits because directly we can't get the information of VLSI each other because it's on the research section. NVIDIA is working on it, like on the placement and routing stuff. So directly we can't find the sources like to understand how graphical networks are implemented for VLSI. So generally we mostly see the software related stuff in it. So just the concept will be same only. So we have to just relate that to our whole electronic concepts. So any doubts related to GNN or like related to industry related or my work, anything I can when in later you can stop me and ask. So these are physical design, like determine the x coordinates, y coordinates, because mostly placement will depend on the coordinates only. Like at what point the cell should be placed and everything, and his data is given to the neural network, and based on that, it will decide. Like based on a timing, because timing should be taken as the one of the main parameter, and based on that only you have to place the cells. And here you want to explain. Once we have the DB, right, synthesis DB, we do the initial timing analysis on the synthesis. In synthesis, we don't have plots actually. So that's why we won't check the whole day. Because unless we propagate the clock, we can't get the whole, because unless it overfits in the because clocks are not there, those are the exact two requirement we don't know. So in the industry channel, what we do in the synthesis state, we mostly check the setup like is it proper or not, when the constraint initially. Once the constraints are clear only, we can go ahead with the design. So initial stage of the project, what we do is we do the constraints clean up, and in synthesis we will check the setup and we check the whole like is it okay or not. Because so for example, so once we have received 1000 NS violation, actually it's a fake violation. Because that much huge violations won't come. That's because of the constraint actually. We have to won't check the timing part is the library setup for like library issue, because of some library issues are there, right? So library setup time will be there. The timing report, if you see the synapse timing, synapse cadence, if you see any of the timing reports, we have the input delay and not to say data path delay, and then the uncertainties and all these things you find in the timing report. So if we have a abnormal uncertainty, that's a library setup issue. So these limits will come from the library so that we have to fix the issue from the library. So based on the particular issues, we have to decide which what's causing the timing violations. And initially, these are all constraint related things we have to close it, and then we have to do the feedback with the PNR. Like for example, I have 100 days timing violation, but the data bar is fully optimized. You can't do anything at that point of time. And what we have to do is we have to check the connections, like to which macros or which channels should be handled. So we can require the PNR to take those cells and we can have a home. We have the concept called home. So you can view the coordinates and you can view the cell hierarchies to which at what point you have to place those cells. So if you view that, those particular cells will sit in particular place as a group. So that all those cells will be closer so that the time will be made. So this is one of the strategies what we use. So based on the violations on each layer, we get the violations, what we have to figure it out. Is the constraint related or the timing related? Like is the PNR fix should be done or the fix should be done for the timing or not? We have to take the decision. So this is routing. Routing is another important thing because we have to heard about congestion, right? Like if it is more congested, if there is no space, we don't have the routing resources. Because even if we have the placement, that should be routed. because the connections are doing the roles only. Right? There are different layers like metal layer, metal 1, metal 2, metal 3, like different layers will be there. Like they are stacked on it. Like some are horizontal layers and some are vertical layers. So these routes we have to always at every point of stage when we deliver the netlist, right? We ask for the connection manufacturer. So is the connection is properly is there or not? Because even you have, if you don't have the connection, if you don't have the road resources, then there is no point of placing those cells because you can't do the connections. There are all for shorts we have, so that we can't take out that. Then they spread actually. The adjacent spaces will be there, right? So they spread the cells so that the proper routing resources will be there for the route. And this is the floor plan, like floor plan will be done visually only because we have the approximate estimate because for example we have 1000 cells for example. So how much area approximate every cell has the how much area we have the approximate estimate. So that he will give with the shape and also there is the top owner will cut the shape actually because some has L shape, some has square shape. We think that all will have square shape only. That's not possible because to effectively utilize the chip area, we see the utilizations of the other blocks also. So that the top owner will cut the shape and he will do the DB of the PNR owners. So that these iterations will happen 2-3 months. So that's why ADA companies are introducing this graphical neural networks team so that the system can train quickly, right? If the program is taking around 4 to 5 months, it's a waste of time for different cycles. Instead of that, if you give to the neural network, it can do it in 1 month effectively. So that the mainly everyone is saying that AI is going to take out jobs, AI is going to take out jobs. For Jensen, who is the NVIDIA CEO of NVIDIA, he says that AI is not going to take the jobs. The people who are using AI will take the jobs. So how effectively we are going to use the AI is the main important. So maybe AI is used for the repetitive tasks because what I observed in my experience, this roadmap will take around 2 to 3 months, and some of the projects are the execution projects. For example, the advancement. Mostly they don't change the floor plan, but they will just see the same floor plan and they make some changes in that one. So this is almost a repetitive task. It's a repetitive task, right? So these kind of things AI can do much better than human. But what we have to focus is what AI can't do. It's a creative thing. Like for example, in timing thing, if there is a false path from one point to other point, like AI don't know that because is it intended or not, we don't know. We have to analyze that is intended or not. Those kind of things, functions are very important. So these kind of tasks we have to make up skills where AI can't come into that. That's what I am also researching on. Because which position AI can't involve, that we have to do. As a humans, to effectively implement that, right? We have to do what AI can't do. So in floaters like VLSI one is there. The VLSI cleanup is one of the same I told you, right? From boundary we get the basic rules. So that's also a repetitive task. If that's get automated, it has just the rules where the properly that base will should be there. So that can be automated. There is some kind of things which can be automated. In the timing also, if you have to track the run, find the run, these are all the redundant tasks what we have. So those things we can automate. So we can focus on more complex design like architecture, where like if you want to run data center, like different SOCs are there. Like mobile has an SOC, and data center has also an SOC, but the applications are different. Data center is used for the training model, like GPUs. CPU will train the huge data and the control of all the data center needs to be done. That's huge. Here, when it comes to the data center, the space constraint is not there. You see, have you seen the data center in YouTube, everywhere, right? It is a huge building. Because of that, we have different racks, right? At the time, just all the NVIDIA liquid page or we have data centers videos. Like Elon Musk XA is there, supercomputer. All floors will have the racks. Racks is nothing but GPUs and they are NVLink actually. So, as the huge data is there, even single chip can't handle the huge data. So that's why we are linking that with the NVLink protocol. If you can search it and open source in the NVIDIA site, you can check that. So that you can interlink one rack to the other rack. If there is huge data, right? Parallel processing is done. There is one video in YouTube, you can watch that. What's the difference between CPU and GPU? Obviously, I have NVIDIA only. Like CPU, at one point of time, it will, what we say, this is a picture, like a smiley will take around 30 seconds to print that image. Whereas the GPU at a single step is the power of GPU is parallel processing. So the artificial intelligence and the machine learning ability needs parallel computing. So that's why actually the other accelerator GPUs are more demand presently. So based on application, different applications has different chips design. So when it comes to mobile SoC, there is no space for it because on mobile only we have to place and integrate there. So the space is very constrained. So you have to design at a particular only how much space if you design, that much demand you have for the mobile. But in case of data center, there is no space constraint because it has a huge building. The main is performance. Main target is performance, so that we should deliver more number of tokens. Tokens will be made. For example, if you request to ChatGPT, let's call one of the tokens. So like you, millions of users are using the so that what is the response time? Like when you type a question that ChatGPT or Llama or any blog, anything, it takes some time reasoning models. So if you see in the DeepSeek also, if you drop down, it will show the reasoning part also, like how the LLM model is thinking. So that speed is evidently dependent on the parallel processing. So the ultimate ability is like a parallel processing and speed of response. So based on one application, we have to decide, and every application has different time constraints, physical conditions, and everything. So based on that, we design to that. So this is one of the things like what I expected, decision matrix and model features. Those are all the matrix form which are computed into the graphical neural learning, and based on the training model, the output is get. So this is a similar one. Here the IC2, it's not this IC2 is that's for the floor planning tool, and FC is there is a fusion compiler which has both synthesis and floor planning. We can tell what happening. People are using fusion compiler because we should have a correlation between the synthesis and PNR, right? Because first the synthesis is done, both synthesis and PNR is done in the same group, so that the correlation will be very good. So that once the floor plan is done, that floor plan is taken as an input of the synthesis, and based on synthesis, the synthesis tool will synthesize the cells like is it a 4 input NAND gate or 2 input NAND gate based on the power, performance, timing, everything. These all parameters it will take into consideration and will do the best cell which use the all the parameters as a best results. It will take and choose and use the output. So these verification testing is equivalence checking. Equivalence checking is actually it's a format like LEC we call. Because you do many manipulations. Like for example, RT will not indicate on manipulation. That is after we are in many buffers and interrupts for growth alignment. For example, instead of one buffer, if you added 2 units, like 2 units we have to add actually, or not to violate the functionality. Because all functionality should be same. Timing owner won't does the functionality, but the RT owner if you want to add some specific feature or anything during the course of, because initially they have some specifications for the particular features. But for example, they want some feature to add in the mobile SoC. They will release some functional EC so that the application logic will be in the functional EC. So that we have to check. At every stage of ECO, we have to check the functionality. It should match with the previous meditation, so that it should be same. So that's called equivalence checking. So what happened, like instead of 2 inverters, it will be 1 inverter, the functionality will be very. So that we check with the formality. So formal verification, that's a key equivalent. Yeah, pattern generation is for, I already told that pattern generation is for all the chip is back, right? So you do the input to the like a patterns you do and you will check that the chip is working for functionally. Yeah. So the power estimation and timing analysis, optimization, all these, like all are applications of GNN. Everything is the common point is the same. What is varying is the parameters, the vertices I told you, what I explained previously, the why the capacity for time will start test and delay and delay, these delays will come. And for power analysis like the leakage power, static power, dynamic power, these functionalities will be. Those things will be integrated into the matrix form and the activation function will vary. So the analysis will be the same and the algorithm is everything will be similar. So these are key applications you can go over. This is a paragraph used by NVIDIA tag. This is the GNN variant for layout actually, layout for reducing the simulation errors. This is one of the paper. You can check offline regarding this. And for power estimation, it's a granite model which has a 8x speed to analyze the power consumption and to reduce the leakage power. And these are the papers for placement and floor building, analog placement, route placement is the GNN for the routing, like for proper routing, these algorithms is used. The trans place is the placement, and the GNN is the circuit related. So these are the overview, and these are the cases. The DPS is also actually the placement algorithm. Mostly the PNR placement routing and synthesis are only the timing is different. So at every point of time, in all stages, timing will be there as an integral part of it. But these stages will be done properly so that the timing should be made. That's the ultimate goal. So these are the future directions, and you should have large data, because I told you that larger data should be there to train this model. That's one of the challenges we have, and we should have more data and storage system, so that we have two more effective algorithms to train these models. So the conclusion is that the CNN is a very effective model, but it has a limitations of the storage problem and data problem. So if we have more effective models for training for CNS, we can actually the work is going on presently in the NVIDIA tools. So thank you. Any questions?